Hello everyone, welcome to a new video. Today we are going to be talking about the Entity Component Systems Architecture, or ECS. I'll be demonstrating the power of ECS by a step-by-step implementation of a simple traffic simulation example that you see here. I'll show you how all of these traffic entities and their behaviors are simulated in the Bevy game engine. ECS is a software architectural pattern aimed at data-driven design. ECS enables modular behaviors through composition over inheritance, preventing problems such as deep or wide inheritance hierarchies, or the diamond problem, which could result from multiple inheritance. Components are pure data containers like, say, position, velocity, or light state. Systems are functions that operate on components through queries, and entities are unique identifiers that tie components together. In the Bevy game engine, bundles are convenient collections of components that can be spawned together. ECS excels at cache-friendly data processing by storing similar components contiguously in memory. For example, in a traffic simulation, a movement system can efficiently process all entities with a position plus a velocity component, such as a school bus or a stroller, while a light system handles entities with light state components, such as a traffic lamp or a school bus, regardless of the entity type. Bevy is a pure Rust game engine that is entirely ECS based. Bevy's ECS includes resources, which are global singleton data that systems can access, and these are distinct from per entity components. Bevy also automatically tracks when components are modified, enabling efficient reactive systems that only process change data. Systems can declare dependencies and run in parallel when safe, with Bevy handling the scheduling automatically. Bevy uses an archetype-based storage model where entities with the same component combinations are stored together for maximum cache efficiency. Systems can query for entities with specific component combinations, including optional components, without components, or recently changed components. The basic structure of any entity in a traffic simulation consists of a position and a render component. Since we're in 2D, our position is essentially a location on the screen. The render component is a plain sprite or image, which is scaled down appropriately. This function creates a sprite component along with a transform component with the given translation and scale. Now we can start to build our individual traffic entities with the help of our sprite function. The first one is a street lamp. We pass the image handle of the street lamp, its position on screen, and its scale factor to the sprite function, which then returns the appropriate bundle. Next is a school bus, and we construct the appropriate bundle like before. The next one is a tree, the same thing, and then the stroller. The next step is to add all of our entities in our setup system, along with a 2D camera. And in the main function, add our setup system to the startup schedule. This will ensure that the setup system runs once when the app starts up. And now when we run our app, we should see all 4 entities displayed on screen. Now let's create a light component which will be used to light up certain entities in our scene. It's very easy to create components in Bevy, and we do that by deriving the component trait. Now let's add some lights to some of our entities. First, we add the lights to our street lamp. What I did here is that I split the part with the light beams from the street lamp sprite into its own sprite. Then all we need to do is to add this part as a child of the street lamp entity. The new child entity would also consist of a light component as well as a visibility component. We do the same for the school bus. Just add the sprite for the headlights to the new child entity along with a light and visibility component. Here is a simple system that I wrote to toggle the visibility of our lights. It takes in a keyboard input resource and a query that looks for all visibility components that appear alongside a light component. This query should return two of our entities only, the street lamp and the school bus. If the spacebar key is pressed, the visibility of the child entities that we just added would be toggled, simulating an on or off light state. And then to our main function, we add the toggle light system to the update schedule so that it is run per update step. And now if we run our app again, we should be able to toggle the lights using the spacebar key. As with the light component, we now define a speed component, which is a wrapper around a float value. This value will represent the horizontal speed of an entity. Now we'll append our stroller entity with an additional speed component and assign it some speed value. We'll do the same to the school bus and add a speed component here as well and assign a reasonable value. The move entities system will then be responsible for moving our entities on screen. It takes in a query with a transform and speed component, as well as the time resource. We extract the time that has passed since the last frame, and for each entity, we calculate the forward displacement by multiplying the speed with delta t along the forward direction. We then add this displacement to the current position of our entity. If the position goes beyond some limits, we simply reverse the forward direction by rotating the transform of our entity by 180 degrees along the vertical axis. And then in our main function, we add the move entity system to the update schedule as well, so that it also runs per update step. And now if we run our app again, we should be able to see the final simulation in action, where the entities with motion move to and fro within some horizontal boundaries, and pressing the spacebar key toggles the lights for those entities that have some kind of lights attached to them. That was it for this video. I hope that you understood a little of how several different behaviors can be quickly composed together in an ECS implementation. Thanks for sticking around till the end, and as always, thanks for watching.